It's the last part in finite difference you have been given, and it's taken from a couple of articles where they have played around with upwind schemes, just to have a sort of a visualization of the effect. What happens when you use an upwind scheme? So the first test case, that was a little bit bad, but I think it's okay. The classical square cavity test case, the default that you have in Sola, but here Reynolds number 1000. Reynolds number 1000, that means we have secondary vortices, and you have a small little vortex up here as well, together with the main vortex, of course. I think it was, yeah, Reynolds number 1000. And the top left, there you have a pure central scheme. The correct solution for the value for the stream function, for the streamlines there, should be roughly 0.1, a little bit above 0.1 in the center. So the top left, that's actually quite accurate. Then you start playing around with upwind schemes. To the right here, you had chosen, what is it, 10% of the upwind scheme as well. So this alpha that we had in the previous lecture, you set alpha equal to 0.1. Then you have 90% is central scheme plus 10% first order upwind scheme. You see the effect. The solution looks quite the same, but look at the value for the stream function. So clearly it's going much slower. The velocities are smaller, although the picture roughly looks similar. Yes, that's true, but not the value for the stream function. He has dropped quite a lot of percentage from what he should be. And down here, there you have 80% of an upwind scheme. There you are down to 0.065, and it should be, the other one was 0.09. So you see the effect, very, very bad indeed. Maybe this one works. Well, works and works. Okay, another example, and again here you have to flip it. Not so easy for either of us. It's not possible to flip it here, but I can draw it easily. It's a very nice test case actually. If you are testing a code, make a tall cavity like this. And then you fill it with incompressible fluid. Could be no matter what, air, water, whatever. And then you say we have one hot side, T1, temperature 1 to the left, bigger than temperature 2 to the right. And here we now are going to have natural convection. So gravity, of course, needed. So the fluid to the left is going to be heated by the wall. It's going to rise up and then make the turn and then go down. Insulated at the top and at the bottom. So that should be your computational domain. Very nice cavity case, 4 walls, very easy. What about the solution? Well, if you have a quite narrow cavity, quite small in the x direction, but pretty tall, you have one analytical solution, but only if. Remember, here we are talking about a driving force in the problem. And the driving force here, that is depending on how the density changes. But we are going to cheat. So we are not going to let the density change at all. But we are going to use sort of the buoyancy effect from hot fluid. He has a driving force upwards. Cold fluid then goes the other way around. And the driving force in the problem here is called a Grashof number. So that's one way to deal with the thermal expansion without actually doing the expansion. So it's still an incompressible flow. And as you see from this Grashof number, proportional to beta parameter, that's sort of the expansion coefficient for the density, and then multiplied with a temperature difference. And the question here, as a driving force, is this Grashof number bigger or smaller than 10,000? If it's smaller than 10,000, the driving force is not so strong. You will have a nice, steady solution that will be something like this. You make the turn here, and then you have one flow going up and one flow going down, and that's it. Very nice. One large vortex. And that's all. If the the Grashof number becomes bigger than 10,000, then this large, narrow vortex is going to break up into many, many small ones. Then you will have the solution looking something like this. Vortex, and then a second the other way, and so on. So here you will have quite a different picture. Have a whole row of these vortices. It's not turbulence, it's still laminar, but these then should be present. For this case, you have a very nice analytical solution given by Batchelor. If you take a cross-section here, the velocity profile will actually go as x to the power of 3. Not all up there, should go to 0. So the v velocity goes like x to the power of 3, and the temperature varies linearly from wall to wall. But that system breaks down when you have too strong a driving force. So these guys here from Finland did a test, and they used 2 different programs running this test case, and they just checked what happened. And here you have the analytical solution by Batchelor. So it's possible to find. It's an old one from '54. So here they used Fluent, and they used feed up. Fluent in those days were more or less finite difference. Well, actually it was finite volume, but a lot of the finite difference techniques were implemented. Very simple code in those days. And feed up, that was a finite element program. And in those days, pretty advanced. And then I tested using 2 different Grashof numbers. 8,500, that is below the critical, so you should have that solution. The other one was close to 15,000, then definitely you should have the other version. And what they plotted looks something like this. So you have plotted here the velocity profile along this line. So to the left, you have both of them for the stable case. And yes, indeed, you have a velocity here and a velocity here, and then 0 in the center region. So you will have this type of velocity profile. Both codes manages quite nicely. Then they went to the other one, this one. And then you see what happens. Fluent in those days used upwind schemes. Remember, Fluent was an engineering tool and still is, so it's very stable. You give him the most stupid input, he gives you an answer, sadly. And in those days, for this problem here, he gave you the same answer. Actually, the effect here, and well, let's go the other way around, never mind that, was spreading it out a little bit. So he took this correct solution and sort of smeared it out so it totally disappeared. He didn't get the breakup at all. Look at feed up to the right. He has it just perfectly, as it should be. So the effect of an upwind scheme can be terrible, smearing out the entire physics in the problem. So this actually is a very good test case. Very easy to set up, easy to implement, and you know what you should get, and the question is, do you get it or not? So of course, Fluent wasn't too happy with this article, naturally. They have made it better. This was in 80 something, so it's an old investigation. But a nice test case, so keep that one in mind if you ever can lay a hand on a code. Now let's jump to the book by Verzigen. And I won't go through it page by page, of course not. So we have done a lot of it already. Well, you can't see this, nor can I. The first chapter, not that many pages, easy to read. Important part all the way down in the chapter 1, discussing a little bit about hyperbolic, parabolic, and elliptic. So you have a short version of it there. And then number 2, also not so interesting for us. A little bit talk, but then, well, some definitions here: consistency, stability, convergence, so on. Also interesting. And a quick description: what's finite difference, what's finite volume, what is finite element. So chapter 3, then he starts with finite difference methods. So we can have a little bit look what he's doing there. Chapter 3 should be here. And model equations. In this book, and in many books, you'll find the same notation used. You have one generic unknown phi. You don't know what it is. Could be temperature, could be density, could be whatever. Normally it's going to be a velocity, and actually a velocity vector. But you write it on this generic form, so he doesn't really bother us. Furthermore, you see the cheat there already. Look at the first term. It's written on this conservative form. You have the derivative in front, dxj, and then you have rho uj times phi, like that. And then on the other side, you have x derivative in the j direction of, and then you will have gamma here being actually a diffusion coefficient. Think of it as viscosity, kinematic viscosity, if you want to have some physics into it. But it could actually be anything. Temperature here, it would be conductivity and so on. So a diffusion coefficient. And then another derivative, like that. And then even a constant, if you like. So typically a model equation for the Navier-Stokes. So of course, the phi there is going to be a velocity. Yes. But then, if phi is a velocity, now say this one is the I component of the Navier-Stokes. Then you'll have ui and ui, like that. Then this one would be in 2 dimensions. It would read something like this. You'll have d dx of rho u square plus d dy of rho u v. So yes, definitely strong form, and to achieve it you have to use the continuity equation. We saw that already. Also, when we keep it in this form, using a generic unknown phi, we have actually linearized this term. So there, one of these velocities, that is this one. The other one is our unknown phi. So here you have a nonlinear term. Here is linear. So you see the cheat. Very easy. And of course, large gamma, yes, normally would be just a constant viscosity. Putting outside the derivative, then viscosity, double derivative of the velocity. The source term here could be gravity, pressure gradient, whatever. It's a steady state equation, so no time derivative. So here he talks also about mesh systems. Here it's all the unknowns are put in the corners. But as you have seen, staggered mesh systems, also something that is used. Now, looking into finite differences, you have central differences, you have backward and forward. So the central definitely looks more like the exact one, but backward and forward differences might be useful sometimes. And then finding expressions for the derivatives, yes, you base it on Taylor series. That is at least the first choice. Finding these expressions, how to create a derivative. And you have several recipes here with different orders. So yeah, you can have a look if you like. Here, in general, delta x's don't have to be constant, they can change, so then the bookkeeping is a little bit messy. Instead of using Taylor series, you can also do the same, assuming that your unknowns, they will change according to some higher order polynomial. You can do that. Then the theory behind it is quite different, so this is not something we are going to look into at all. It's possible to do it, and here also you can have the discretization schemes quite compact. Although you see how they've done it here. If you are up into the third order accuracy, you're going to need some neighbor and the next neighbor and the next neighbors as well. So not so easy. Fourth order, you're going 2 steps in each direction. So then your discretization star is going to be quite big in space. That, of course, also with ordinary finite differences based on Taylor series. It's possible to make them smaller with these compact schemes, mixing it up a little bit, but I won't go through any of this. You can have a look for it yourself if you are interested. So central differencing schemes, CDS as he calls it. and then PADE, meaning or based on polynomials. Yeah, non-uniform grids, not so interesting. Second derivative we have seen already. So one way to construct it, double derivative, you take one derivative on each side of a central point divided by the distance. Fairly easy. That's one way to achieve it. And we have the standard formula that we have used many times already with the central scheme, the two neighbors, and minus 2 of the center point divided by delta x squared. Also mixed derivatives and so on and so forth. Not so interesting. The boundary conditions, they can be a pain. But you find, if you search for it and you need it, you need, say, a derivative on the boundary, and you want it to be of high order accuracy. Then here you have a fourth order accurate scheme, but you see how many points you have to use. The boundary point, number 1, the one it's where you want the position for the derivative. Then you have to go 5 points inside the domain actually to have that kind of order. Can be a little bit messy to program. A lot of bookkeeping. And then finally, after having a discrete version of your partial differential equation, you get a bunch of algebraic equations which everybody almost is using the same stencil, the same notation as Patanka did in his famous book from 80s. So you have east, west, and the center point P. And in 2D, north and south. And in 3D, you go top and bottom as well. And then the different points here, northwest, northeast, and so on. And you even have north-north and south-south if necessary, if you have to go 2 points away. Quite standard notation for a structured mesh. So almost everybody is using this. Also, in the end, you get an equation system here just in a matrix form. But what we normally use is something like this. Coefficient A, and then your unknown phi at a different location. So you'll find a lot of these algebraic equation systems in actually any numeric book in CFD. Almost everybody uses this notation, which then has to be solved. The other, yeah, not so interesting. Spectral method, that's not something we are going to look into. It exists and it is very fancy. So within one cell you sort of use, well, not one cell, your domain, you use a Fourier series to represent all your derivatives, a discrete Fourier series. The theory behind it can be a little bit heavy mathematically, but the spectral methods are in general more accurate than anything else. So if you look at the discretization error, it's possible here to plot as a function of a sort of an artificial wave number. So the spectral code here actually fit perfectly with the exact solution. Second order central scheme and fourth order, they are beginning, but they require quite small delta x's. So even if the delta x's becomes too small, they're still wrong again. So they are not so good. They can't really compete with spectral methods. And we have one group here, spearheaded by Rönnqvist, Professor Rönnqvist in numerical mathematics. He's dealing with finite element spectral codes. So one cell being one element, you have an entire spectral formulation for the variation inside one element. Very accurate, very complex. So nobody else understands it but him. But if you're interested, you can go and talk to him. He would love to have a PhD student, I can tell you. But it's very hard. The math is rather heavy. So not the easiest place to start if you're interested in CFD. But it's very accurate, quite impressive what he can get out of it. And he doesn't understand why people do anything else, like finite difference, finite volume. In his eyes, that's just kids' play. But
how high can you go in terms of Reynolds number with that code?
I'm not sure. I'm not familiar with it. I haven't touched one of his codes at all. But I think you can do the same as in any other code. And I mean, in Reynolds numbers, if you increase the Reynolds number too high, okay, then you need a turbulence model, as he also needs, of course. Then you have to design turbulence models for spectral codes. Yeah, if you want another PhD, then you can't take more than one, you know. You don't have to stop at one PhD. Let's go to this example. It's a very classic example that we can play around with. So here you have the problem. So let's have a look at that one. It is a one-dimensional problem, and it's a steady state problem. So we don't have any delta t involved. So according to what we learned so far, we shouldn't have any stability problems. Shouldn't be any trouble solving that equation directly. So we have it on the form, what is it, ddx of rho u phi equals, and then on the other side, ddx of gamma d phi dx, like that. So now make a central space scheme of this one. He uses CDS, central differencing scheme, and he uses upwind differencing scheme, CDS and UDS, central and upwind. So what will we have here? What do he use? Uses J, I think. No, he uses I. That's okay. Thank you. Stop. What happened to the mouse? Here we are. For simplicity, for us, I would say we could do it a little bit more easy here. First of all, it's a one-dimensional problem. You don't have to use partial differential. You could use ordinary differential if you like. Also, we can treat the gamma as a constant, put him outside here and call him viscosity, then we know what it is. And here we assume the velocity field is given. We know u. He's a well-known number and he's constant, just to make it easy. Not a problem there. So then we can rewrite this one as rho u, and then we have du dx equals, and then on the other side, kinematic viscosity, double derivative of, well, if you want phi, be my guest. Just so we have this velocity at something else. So we can use phi as the unknown, that's okay. What will the CDS scheme look like? Well, you will have rho u, and then you multiply with phi I plus 1 minus phi I minus 1 over 2 delta x. And the double derivative, as before, I plus 1 minus 2 times the center point plus I minus 1 divided by delta x square. There you have the central scheme. What about the upwind? Well, the upwind, that's only the term where you have a velocity outside, or inside if you like, but you have to decide is he positive or negative. So here we say this guy here, he is bigger than 0. So the flow is going to the right. That means the first order derivative can be written rho u, and then we say phi I minus phi I minus 1 over 1 single delta x equals, and then the same thing on the other side. So there I have my two stencils. For this problem, now a one-dimensional problem, we have been given an analytical solution. You have, for an x distance of L, you say phi is phi 0 in the beginning, and he ends up at phi left. Now for simplicity, of course, you can say phi goes from 0 to 1 over a distance from 0 to 1. So you can normalize everything if you like. That's quite okay. And the solution is actually plotted here based on what's called a Peclet number. And this Peclet number, what will it be? Peclet number, it is rho u length over this gamma, which we then instantly recognizes as a Reynolds number. So here you'll have rho u and then same length scale, but we use not that viscosity, we need the other one, sorry. There we have it. So this would now be a bulk Reynolds number in the problem based on a length scale big L. That is quite okay. For what we're also going to need is a cell Peclet number, then based on the length delta x. So that should now read rho u delta x over gamma, or if you want, use the Reynolds number based on a length scale delta x. Cell Reynolds number, cell Peclet number. So should we have any stability issues here? Should that be any problems? Well, we don't have a time, so it's just a question of solving this equation system actually, which is a very nice, neat three-diagonal problem. So yes, you can get a solution using a direct solver if you like. Shouldn't be a problem. And I think I did that. Here, solving the problem. It's very small. But you solve the problem here using a TDMA algorithm. That's the Thomas algorithm for a three-diagonal equation system. if I recall correctly, isn't it? Yeah, I just call a routine called TDM. I'll give it to you later so you can have a look at it if you want. He solved just then this equation system here when you set it up. All your unknown fees. I mean, first you write it equal to 0, this equation system, and then you can set up the coefficient matrix A multiplied with the vector of all your unknowns equals a right-hand side, and then solve it using the Thomas algorithm, which then actually is just some back substitution of all your equations. So it's a direct method. If you don't want to use it, you could use MATLAB's built-in backslash, directly solving an equation system. So yes, that's quite possible. What they have used here in the code, you choose a number of unknowns, of course. Let's see, all the programming here is a little boring. What's interesting is the results. So here, first case they have been running, Peclet number is 50, Reynolds number is 50. That's the bulk Reynolds number. But if you look at the scale here, if you want to use a delta x instead, well, a non-dimensional delta x will be delta x over L. So if you just multiply this one with a delta x, then you have the cell Reynolds number instead, or cell Peclet number. So here you specify the Peclet number, and here you then get the local Peclet number by just multiplying with delta x. That's the whole thing. Setting the boundaries 0 and 1. And then we have the exact solution as well. So if we now try to run this one, we should get the same as, I hope, as the figure that we have to the left there. And indeed we do. And we have some very strange results for the central scheme. It oscillates a lot. While the correct solution, the yellow line there, should be nice and smooth. And now the UDS, well, he's sort of have the correct idea at least. But the differences here, it's quite big. So he's stable, but he's not a good solution. But here we actually got an unstable solution, more or less. How can we see an unstable solution here from these equations? Well, if you rewrite them, let's see now, we multiply these equations with delta x square divided by the viscosity. Both of them. Then what happens? Well, here then to the left, what do you get? You will get the cell Reynolds number, rho u times delta x divided by the viscosity. And here I have 1/2. So the CDS scheme will now read cell Reynolds number, and then multiply him with phi I plus 1 minus phi I minus 1. And then I take this one also on the other side, so you'll have minus phi I plus 1, phi I, and then finally phi I minus 1 equals. And then on the other side, actually what we have then is not 0, but higher order terms, of course. But when we are trying to solve it, we call him 0, of course we do. Now, write this one on a form that you could program it if you want to use an iterative method. Very simple. Just focus on the center point. Isolate this guy. Put him alone on one side. The center point. Phi I equals. So it's a little reorganization here. Of course, you don't have to take the center point, but normally it's the most stable version of any iterative scheme focusing on the center point. Absolutely the smartest one. So here you see I have minus minus, so I have to keep him on this side and then now throw everything else on the other side. So what will we have? Phi I plus 1, he is multiplied with what? Well, let's see, minus minus, so he's staying here. Throw him on the other side, he will be plus 1. That's him. But here you will then have minus the cell Reynolds number. Actually, we are missing 1/2 here. Yeah. So I will have 1 minus cell Reynolds number 1/2. That was I plus 1, these two guys. Then you do the same with phi I minus 1. He will have 1 here on the other side, he will be positive. But then minus minus will now be plus cell Reynolds number 1/2. Right? So now use the max mean method on this one. Although max mean method actually was meant to be used by a time developing code, meaning stability for delta t, you can still use it here. If you treat this one as sort of an iterative idea, we have to do this many, many times. Finding a new value based on old values from the now, not the previous time step, but the previous iteration. Can we use the method, max mean method here? Well, you add the coefficients and indeed you get, do we get it? Yes, I have a 2 here. I've forgotten that one. So we have 1/2 here. Add the coefficients and yes, you get 1. So you could use the method. Next demand, all coefficients has to be positive. This is not a problem, always positive. This one might be the problem. So here we will now have the cell Reynolds number must be smaller or equal than 2. That is the demand that we get. Cell Reynolds number, or cell Peclet number if you like, has to be smaller than 2. Now to the case to the left, that is the central scheme with cell Reynolds number 50. How to find the bulk Reynolds number. Bulk Peclet number is 50. You just multiply with delta x, and then you have the local cell Peclet number, and you see he is 5. So we have violated this criteria. He is 5, so no way he's going to be stable. And indeed he wasn't. For the upwind scheme, what happens then? You do the same, but now we're choosing this scheme instead. What will be the difference? Well, it should read a U here. This one here should now read only I. And we should not have 1/2 anymore. It should only be 1. Like that. But that is the only difference. You keep the double derivative exactly as it is and multiply with this one. Down here we missed the 2, but else it should be the same. Okay? So now we have to isolate UI. And I have one there, but now I have another one here as well. So now we have to rewrite this one a little bit. What will we get? I get a coefficient in front of my ui also. Let's see, minus minus on the other side becomes plus, no, on the same side, sorry. He will be 2. And this guy, he will be plus the cell Reynolds number. That will be the coefficient in front of my center point. What about the other points? I plus 1 here. Well, he has only 1, so this one is not here anymore. Phi I minus 1, well, he has the 1 here, and then plus 1 entire cell Reynolds number. There we have it. Again, can we use the method? The sum of the coefficient is now this one plus this one, 2 plus the cell Reynolds number, divided by the exact same thing. Yes, the sum is 1. You could use the method. Next demand, all coefficients should be positive. And indeed they are. So this one, unconditionally stable. Which is actually the case. So for this problem here, if we increase the cell Reynolds number to 500, and we look at the solution, the central scheme becomes very, very bad. Yes, indeed. Now we really has violated the criteria. Our local cell Reynolds number now should be as high as 50, I think. Yeah. But if you look at the upwind scheme, is this one actually, he is still stable. Now he is far, far, far from what he should have been. That's the one small down here somewhere. It's hard to see them, isn't it? Color map jet. Does that help? No, not much. Well, believe me, he's almost in here. So the higher Peclet number, the higher cell Reynolds number, the stronger this shoulder, you might say, will be. So that the harder the turn will be just down and there in the corner. And he's far, far from it, of course he is. But he's stable, unconditionally stable. But the error is huge. While the central scheme, he is way off. Okay, if we now go back to the one we had here, jumping up and down a little bit, how can we get the central scheme to be stable? Because the central definitely is more accurate, but we can't have this up and down motion. Well, actually, there's only one remedy. Use more cells. You have to sort of resolve the spatial resolution. So now I double the number of cells. Still not so good. It tends goes negative here, but still you see the cell Reynolds number is 2.5. We have still violated the criteria, so we need more cells. 31 then. Then we're talking. So now the correct solution and the central scheme are indeed very, very close. My cell Reynolds number is now 1.67. So now we are good to go. The upwind scheme, yes, you get a solution, but the error is quite big. I think he shows the same here as well. Yeah. Here he uses 41 cells So the upwind hits very nicely to the left. The central hits nicely to the left. Upwind to the right. Outward quite big. I'm continuing a little bit more, but then I have to run. I have a plane to catch, so we skip the break. It's not that much more I wanted to show you here. I think he stops in this discussion. Yeah, he plots the arrow, and here, of course, in a log-log plot, you can see that the arrow with the slope there, the second order scheme, central differencing, goes with a slope of 2, and upwind goes with a slope of 1, first order. He also plays around with a non-uniform mesh, which of course is a natural in this problem when you have the solution looking something like this, very sharp gradient here. Of course, here you need a lot of cells, but here they could be pretty big. So a constant delta x here is not a good idea, actually. Yeah. Now, can we see what this upwind scheme has done? Yes, I think so. I think so. Let's have a look at the modified equation. We have the upwind here. Find the modified equation. Modified equation. How can we do that? Well, here is not so difficult to finding the modified because we don't have any time derivative into the problem at all. So that should be a little bit easy. But we need the Taylor series here, inserting for I minus 1. What was the Taylor series? Let's rewrite this one. And we don't need this one either. Phi I plus minus 1 equals phi I plus minus delta x, phi derivative plus delta x square half phi double plus minus higher order terms. I don't think we need more than the two first, actually. So if we now insert the series here, what do we get? We will have rho u divided by delta x, and then ui minus the negative series. This center point disappears. We will have minus this guy. That is quite okay. So then we will have a delta x and a phi derivative. Of course, here we will get the original equation back, so that's nice. The next one, minus, but here is plus. So that will now be something negative. And here should read delta x square half phi double. And then even higher order terms. Equals, then we have to do it on the other side as well. Mu delta x square. The sum of both the Taylor series, the positive and the negative, minus 2 times the center point. The center point, he will fall, plus 2 of him, and we have minus 2 of him already. Then we have the sum of these two guys. They will cancel each other out. One is positive, the other is negative. This one, he will survive. He will survive. And I will have him twice. So I will have 2 times delta x square half of phi double. Next one, the third order term, he will cancel himself out. One will be positive, the other is negative. So the next one I get here will actually be phi 1, 2, 3, 4 multiplied with delta x to the power of 4. What I get here is delta x power 3, phi 1, 2, 3. That's my higher order term there. Now write it out, and you will see you get the original partial differential equation. Yes, indeed. That will be this term and this term. So we can write it like this: rho u phi derivative, that's him, weight with him, equals, and here you will have 2 times him disappears, he disappears. You will have phi double derivative, and you will have multiplied with the viscosity. And now this one shows up. Throw him on the other side. He's negative here, so he will be positive on the other side. And what does he read? Well, we have rho u delta x 1 and then divided by 2 phi double, and then higher order terms. This is what happens. We add viscosity into the problem. How much do we add? Well, you can rewrite this one a little bit. Take the viscosity outside, mu double derivative, and then you see you have 1 plus the cell Reynolds number half, plus even higher order terms. Meaning a cell Reynolds number of 2, which was the stability limit for the central scheme. Using an upwind scheme, it's unconditionally stable. You get a solution for cell Reynolds number from 2 and even above. But you see what you're doing. Doubling or tripling or quadrupling the viscous term. Terrible, awful. Never use it. Don't use it. Okay. Any questions to that one? If we did the same now with this one, what do you get? Modified equation, what will it be? Well, it will be roughly the same. Rho u phi derivative equals, but on the other side you will have something else here, mu phi double derivative, and then something with delta x square, including triple derivative. You don't get any additional double derivatives into the equation system. So he doesn't include any more diffusion. He includes adode of order delta x. First order upwind, of course the adode is of order, delta x square. Here is the adode of order delta x. So central scheme, yes, much better, but sadly much more unstable. Hard to find correct solutions. So I'll put out this code for you, and then you can play around with it as you like. Go back to the original, like that. So here I've taken the coefficients more or less directly from the book. So I think I did it correctly, but you can check it if you like. We have some other examples as well, but we will then address finite volume, which then will be the start next week. Any questions from you?